Okay, we're going to look at finding the mantissa and exponent and floating point binary. So the real number decimal value that we're working with is 64.5, and we're first going to try to find the mantissa and exponent and the sign, obviously, and represent them. And then we're going to represent it all in 32-bit binary. So the very first thing I did to try to solve this is we're going to convert the value of 64. So there's a couple ways you can do this. One of the ways is, because we're converting to binary, we can continuously divide 64 by 2 and build our binary value. So I'm going to do that quickly on the side here. We have 2 goes into 64 32 times, okay? And there'd be no remainder, so that means the rightmost digit for the binary would be 0. We then take the quotient and we divide that by 2 again, and that goes in 16. Again, no remainder, so we put 0 as a remainder. We then take 16 divided by 2, we get 8, remainder 0. We take 2 divided into 8, we get 4, 0 remainder. 2 divided into 4 is 2, 0 remainder. 2 divided by 2 is 1, 0 remainder. And then finally, 2 divided by 1 is the value of 0, but we have a remainder of 1. So here we go. We have 1, 2, 3, 4, 5, 6, 7 digits, so 6 zeros, and the leftmost digit being a 1. We can also check this by just quickly doing some mathematics with the 2 exponent. So we're going to represent each of these as powers of 2. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, and 2 to the power of 6. Any place that there is a 1 digit, we're going to multiply by that power of 2. And that value we multiply by 1, and that will represent our decimal value. So we have a whole bunch of zeros here, so these represent absolutely nothing. 2 to the power of 6 is actually 64, and 1 times 64 is 64, so that worked out wonderfully. You can check this quickly by also doubling these values. 1, 2, 4, 8, 16, 32. Great, 64. So we got that part of it correct. The next thing we want to do is convert the decimal 5. We can do that by multiplying by the value of 2. So we're going to take 2 and we're going to multiply it by 0.5. That ends up with the value of 1. Oops, 1, 0, 0. So our binary value to the right of our decimal place is a 1. And because there are no values to the right of the radix or the decimal place, we don't continue the process. So here we go. This is our binary representation. So we're going to put this entire number together, and we end up with 1 followed by 6 zeros. So 1, 2, 3, 4, 5, 6. And then we have our radix and 1. So here's our binary representation. But we want to do floating point. And with floating point, we need to have a digit that represents the sign. Maybe we can do that in purple. We need 8 digits that represent the exponent. Okay, and we'll eventually need, what we got, 9. We're going to need 23 digits that represent the mantissa. Okay, but before we get to that step, there's like a little formula we can also use to represent this, and it is the sign multiplied by the mantissa times 2 to the exponent. So we're actually going to try to convert into this first. Let me bring this over. Okay, so we had our binary value here. It was 1 followed by 6 zeros, 1, 2, 3, 4, 5, 6, and a radix, and then the value of 1. Because our 65 or 64.5 was a positive value, positive values are represented by the binary digit of 0, and negative values are represented by the binary digit of 1. So in this representation of our little formula here, our sign, in purple here, so our sign is going to be a 0. We're going to multiply by the mantissa. The mantissa here is, all we're going to do is we're going to move this decimal value over, and our new mantissa is going to be 1 followed by 6 zeros, 1, 2, 3, 4, 5, 6, and then finally a 1 value again. And then after that, we multiply by our base 2 to the exponent. Now the exponent is the direction and distance we've moved in orders of magnitude. So we move to the right one value, which means we are going to have a negative. So anything to the right is a negative movement, and any movement to the left here would have been a positive exponent movement. So we move to the right one, which gives us a -1 exponent. So this is our floating point representation of our 64.5. But in this question, they wanted us to actually convert it all to a 32-bit digit value. So there's still another conversion we need to do. We have the Mantissa. That is a 1, 0, 2, 3, 4, 5, 6, and then a 1. And then technically we've got to fill out the rest of the digits here. And I think there was 8 here. We've got to get to, let's say we're starting at 0. The 22nd value, all of these would be zeros up to the 22nd value. So if we're representing a 32-bit binary representation. The sign is also a 0 value. The exponent is what we have to calculate. And because our exponent is a -1, okay, we can actually convert. We'll find the positive value of it, and then we'll use the 2's complement to find the negative value. So I'm going to use, actually you can use the exact same way we had done before. If we have the value of 1 and we divide it by 2 to convert it to binary, ends up with 0, we have remainder 1. Well, look at that. Our binary representation is just 1. I can put a couple zeros in front, and in fact, because the exponent represents 8, I think there's 8 bits represented, or 8 bits that you can represent the exponent with. There's 1, 2, 3, 4, 5, 6, 7, 8. We have all zeros in front of those. And we'll just double check again with our base 2 exponents to the power of 0, to the power of 1, 2, 3, 5, 6, and 7. And we know that represents 1, 2, 4, 8, 16, 32. Getting a little squished in here. 64 and 128-bit. Great. That value of 1 times 1 is 1, so we've double checked, that works out, but we need to use the 2's complement of this. Well, the 2's complement of this 8-bit representation, we can flip all the values and then add by 1. So I'm going to do it over here on the left. We have 1, 2, 3, 4, 5, 6, 7 zeros and a 1. With the 2's complement, we would invert all of these. Okay, and then we're going to do a little binary addition and add a 1. And lo and behold, our exponent ends up being just 8 bits, and every binary value ends up being a 1. So 1, 2, 4, 5, 6, 7, 8, and there's our answer. So our answer in this question is the sign is equal to the binary digit of 0. The exponent is 8 representations of 1. 1, 2, 3, 3, 4, 5, 6, 7, 8. That gives us 9. And then we need 23 representations for the Mantissa. And I'll kind of start over here. Mantissa should have 23 representations. I'm going to start on the right side because I know it starts with a 1. Then we have 6 zeros. So 1, 2, 3, 4, 5, 6. Is that right? Followed by a 1 binary digit, and then all the way to the end, the rest of these digits, because it's 32-bit again, would actually be zeros. So I'm just going to take stock here so I don't lose track of how many zeros I'm putting. 1, 2, 3, 5, 6, 7, 8. Okay, we're on our 8th, so 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There you go. That would be the value, the 23 binary digits that represent our Mantissa.